Hello, welcome to PhysQuest. So this is the solution video for CSIR NET December 2019 Part C, question number 30. The question is, for a crystal, let phi denote the energy required to create a pair of vacancy and interstitial defects. If n pair of such defects are formed and this n is much less than capital N and capital N prime, where n and n prime are respectively the total number of lattice and interstitial sites, then n is approximately 4 expressions are given and we need to choose the correct option here. So let's get started. So this question comes from the section solid state physics and the concept involved here is defects. So first of all, you must now, when we talk about a crystal lattice may seem perfect, but in reality crystal lattice is not always perfect. There are certain imperfections in their atomic or molecular arrangement which are called defects, and defects can be categorized into 4 categories, that is point defect, which is 0 dimension, then line defect, then surface defect, and then volume defect. So now here this is a crystal and this question is based on point defects. So now point defects, when we talk about, they are also various types. Now first of all, suppose when there is an atom is not at its usual place, that is it's missing, then it's called vacancy. Similarly, when an atom is in a wrong place, then other than its lattice point, it's called interstitial. Then when there is a impurity atom is present or replaced in the original atom, that's called substitutional impurity. Then when there is an impurity atom is placed in an interstitial site, it's called interstitial impurity. These are the 4 categories of point defect. Now here the presence of these type of defect can happen in 2 ways. One is called the Schottky defect, where the original atom is moved away from the lattice point out of the crystal lattice, creating a vacancy there. Then another way is called the Frenkel defect, where the crystal atom is moved from the original position at the point to an interstitial position, creating a vacancy as well as a interstitial site. So this actually creates a vacancy as well as an interstitial defect in case of a Frenkel defect. So in this question we have n prime number of lattice sites and n prime number of interstitial sites. Now here the defect create a pair of vacancy and interstitial defects. So this situation which is presented here is the case of a Frenkel defect. So in the question there are n pair of defects, which implies there are n number of vacancy and n number of interstitial defects. Now we need to calculate here the energy required to create these number of defects, and the condition is that this n is much less than both capital N and capital N prime. So now whenever a point defect is formed in a crystal, then its internal energy increases. So therefore, and because of this, the enthalpy of formation is positive, and this also increases the entropy of the system. So in what will happen is, in this scenario, the Gibbs free energy of the system will decrease, and Gibbs free energy, which is given by the expression delta G is equal to delta H minus T delta S, this has to be minimum at equilibrium concentration. So in order to find out the equilibrium concentration, we must check the Gibbs free energy at its minimum value. So now here in Gibbs free energy is an important criteria to find out what are the pair of defects formed. Now here in the delta G formula or the Gibbs free energy formula, 2 are the important aspect. What is the enthalpy and the entropy? So let's discuss them one by one. So first of all, let's talk about enthalpy. So in the question it is already given that the phi is the energy required to create a pair of vacancy and interstitial defect, which by definition enthalpy is actually the energy required to form energy of formation or enthalpy of formation. So here phi, which is the energy required to create a pair of vacancy and interstitial defect, is actually your enthalpy. So in the formula of Gibbs free energy we can replace that. So delta G will be equal to n phi minus T delta S. Now why n phi? Because phi is energy required to create a single one pair of vacancy and interstitial site, and there are n pairs such defects. Therefore the enthalpy will be n phi. Now let's talk about entropy. Now how to calculate the entropy? So here entropy is given as delta S is equal to K into ln W. W is the probability. So probability in which the n number of vacancies has to be distributed in n lattice points and n number of interstitial defects to be distributed in n prime number of interstitial sites. So first of all we need to calculate the probability. So the probability will be, in that scenario, it will be, the expression will be W is equal to n factorial divided by n minus n factorial into n factorial multiplied by n prime factorial divided by n prime minus n factorial n factorial. So when we put this expression into the entropy expression, the expression will be like this. So first of all, how to solve this lengthy expression? So here what we need to use is, we need to use the Stirling's approximation. So when we use the Stirling approximation by opening the bracket using the logarithmic rules and as well as applying the Stirling's approximation, when we expand this whole thing, this will be an expression like this. So when we put this expression into the expression of the Gibbs expression, that is delta G, this will be, expression will be like this. So we will get an expression of delta G ultimately. Now our purpose is here, see, at equilibrium concentration the delta G is minimum, which I already said. So delta G is minimum means del of delta G by del N is equal to 0. So what we have to do is, we have to differentiate the expression with respect to n and set it as 0, and then we can ultimately get, by solving this, we get an expression of n. So here when we do that, upon differentiating it and setting it 0, ultimately we get phi minus kt ln n minus n into n prime minus n divided by n square is equal to 0. Now here one condition is given, that this n is much less than both capital N and capital N prime. So that means n minus n is approximately equal to capital N and n prime minus n is approximately equal to n prime. So in place of n minus n and n prime minus 1, we can put this expression, and ultimately we will have phi minus kt ln nn prime divided by n square is equal to 0. So now this we can also write as, so this will be equal to phi minus kt ln square root of nn prime divided by n whole square is equal to 0. So by the rule of logarithm, this expression will be phi minus 2 kt ln n square root of nn prime divided by n is equal to 0, and ultimately it will be phi by 2 kt is equal to ln nn prime by n. So when we finally solve it, this will be lead to an expression of n which is equal to, n is equal to square root of nn prime exponential of minus phi by 2 kt. This is the final expression we have got by upon solving it. So now let's check the option. So when we check the option, we can see that option A is matching with our result. So correct answer for this question is option